Hello everyone, welcome back to the series of lecture for the course Discrete Mathematics. So we are in the elementary number theory unit and we have discussed what is GCD, what is LCM, how to find that. So we'll continue the same thing and then related to GCD we'll learn few new things and we'll also learn that what is the like inverse modulo some number. Right, so let us see. Now, GCD as a linear combination. What is that? If A and B are positive integers, then there exist integer S and T such that GCD of A comma B is equal to SA plus TB. So then this GCD you can write it as a linear combinations of GCD of AB, you can write it as a linear combinations of the numbers A and B, SA plus TB. So S and T are some integer. So this will always happen. Now I will take some example and do, and then later I will give you some examples that you will solve. So we know that, okay, maybe what we'll do. So the same example we'll take that we have done in the previous example. So this 75 and 60. GCD of these two, we'll write it as linear combinations of this number 60 and. So what to do, how to proceed? We'll do the similar kind of way that you have done in Euclidean algorithm, finding GCD using Euclidean algorithm. The same process we'll do. What is the largest among them? 75. So what we'll do, 75 is equal to 60 into 1 plus what? It is 15. Then what you will say, 16 is equal to 60 is equal to 15 times 4 plus 0. So we got this is 0. So the GCD will be this number, the previous number. Right? How? Because GCD of 75, 60 using Euclidean algorithm, you say that GCD of 60, 15. That type itself we have done, but if I apply the Euclidean algorithm in the next equation, so it is 16, 50 is equal to GCD of 15, 0, and which is 15 itself. So if I do this thing, equate the equations, we'll get GCD of, maybe I'll say that GCD of 75, 60 is equal to 15. And here this example I have taken, it's a very easy example I have taken. And you can easily see that this 15 you have written, already it is in this form, that 75 minus 60 times 1. Right? So basically it is 75 into one integer, which is 1, plus 60 times another integer, which is minus 1. So it is the linear combinations of 60 and 75. Right? So what is S here? A is 75, B is 60, A is 75, B is 60. So this is A, this is B. What is S? S is 1 and T is minus 1. So we have written GCD of 75 and 60 as a linear combination. So the example what we have taken, it's a very easy one. One step we have done. We'll do one more example. There you will see that you have to do 2-3 steps. But any GCD of any two positive integer, you can always express it as a linear combinations of SA, like the numbers itself. And that has a lot of significance that I will show you after some time. Now, do this example. Express GCD of 102 and 202, which is actually 2, as a linear combinations of 102 and 202. So what to do? We'll do the same process. So 202 is actually equal to, we'll do it as 102 into 1 plus what? It is 100. Next step, 102 is equal to 100 into 1 plus 2. And then 100 is equal to 2 times 50 plus 0. 2 times 50 plus 0. So our exam problem is done. And we can always see that because I have got that 50, 0. So GCD is actually that reminder I got it 0. So we'll stop the algorithm. And we can see that GCD is 2 by using the previous method. So we have GCD of 202, 102 is equal to 2. Now, how to express this, how to make it as a linear combination? So this 2 is equal to basically 102 into this. So I'll write this value. So this 2 is equal to, from this expression, I get 2 is equal to 102 minus 100 into 1. Still my, these things is not done, right? Linear combinations of the number 202 and 102 have to get. But the previous example, in the first step itself, we got the answer. But here we have to do one more step. Like 10 to 1 factor I got, but I have to change this 100 something. But what is the value of 100? Value of 100, I can get it from this equation. So I'll apply this 100 value. So 102 minus 100 is equal to basically 202 minus 102 into 1 into 1. So this is, if I simplify it, 102 minus 202 minus 102 into 1. So this is same. So if I just simplify again, 102 into 2 plus 202 into minus 1. We got S is equal to 2 and T equal to minus 1. And you see that GCD of 202 comma 102, which is actually 2, and you have written as a linear combinations of this number 102 and 202. What are the coefficient? S is 2, T is minus 1. Our job is done. Right? Now, this has significance that I will tell you that this method will also help me to find out how to find the inverse modulo positive integer. That I'll discuss. So before going to that, I have few results which are very important one that I'm going to tell you without the proof. So these are some important lemmas related to divisibility and prime. What it says? Let n be a positive integers and a, b, and c are any integers. If AC congruent to BC mod n and GCD of C comma n is 1, then you can cancel this. You can say, then I have A is congruent to B mod n, right? So if GCD of this C and this n are 1, then you can always cancel this C and you will say that A is congruent to B mod n. Clear? So this is one theorem that you should know it, that in many places you may have to use this. Okay, next. We have two more results. It says that if A, B, and C are positive integers such that GCD of AB is 1 and A divides B into C. GCD of A and B is 1 and A divides B into C. Then you must have A should divide C. A should be definitely divide C. Correct? So if you have A, B, C are all integers, positive integers, and GCD of A and B is 1, and if you have A divides B into C, definitely A should divide C. Then next, this is the generalization of the previous one. If P is a prime and P divides A1, A2, An, where each AI is an integer, then P must divide exactly one of the AI. P should divide one of the AI. Not exactly, P should divide one of the AI for some i. Correct? So if P is prime, that AI can be anything, but this A1, A2, An, if you have that product, then P should divide one of them. This is another one. So these results are helpful to find out, like to do some examples. Now what we'll have, we'll discuss what is inverse modulo positive integer. So what you have, now we all know that what do you mean by multiplicative inverse? We all know, right? Multiplicative inverse of A is what? If it is B, then your AB should be 1. Then you will say na, that B is the multiplicative inverse of A or A is the multiplicative inverse of B. So the inverse modulo thing, that is also similar kind of thing, but under modulo thing. What it says, that B is said to be an inverse of A modulo n if AB is congruent to one module, right? So B is said to be an inverse of A modulo n if AB is congruent to one module. So B is said to be inverse of A modulo n if AB is congruent to 1 modulo n. Clear? So this is the definition. Now we'll have something called some theorem we'll have how to find the inverse modulo n. This theorem will help us to get that. If I have A and N are relatively prime integers, if I have A and N are relatively prime integers, relatively prime means their GCD should be 1 with n greater than 1, then an inverse of A modulo n exists. Inverse of A modulo n exists. Because there you may not have guarantee that A, B, like B, the inverse modulo A exists. You may not have inverse modulo n. But if your GCD of A and N are 1, then definitely you have an inverse modulo a n, right? Inverse of a modulo n definitely exists. Furthermore, this inverse is unique modulo n. This inverse is unique modulo n. So this proof is not much required, but I will only prove the first part of it. I will only discuss the first part of it. Now you see that you say that a and n are relatively prime integers. That means what? Their GCD is 1, right? And in the previous example, in the previous theorem, we have learned that GCD between any integer can be written as a linear combinations of these integers. So since GCD of a and n is 1, then there exists some integer s and t such that GCD of which is 1 is equal to sa plus tn. That means linear combinations of a and n. So we can have this. Now this implies that sa plus tn is congruent to 1 modulo n. Why? Because this value sa plus tn minus 1, it is 0, which is divisible by any number. So it is divisible by n also. So we can always say that this n divides this one, n divides this. We can always say that n divides this because it's a 0. Now if n divides this, that means I can have sa plus tn is congruent to 1 modulo n. Right. Now here n is in factor. So if n divides this, I can always say that definitely n divides sa minus 1. If n divides this, sa should divide sa minus 1 as well, because n will give you remainder 0. So sa minus 1. And therefore we have, I can say sa congruent to 1 modulo n. Right? And if I have this expression, what does it mean? It means s is the inverse of a modulo n. S is the inverse of a modulo n, because this is the definition. B is said to be an inverse of a modulo n if a into b congruent to 1 modulo n. So S is a inverse of a modulo n. And this part is the uniqueness proof, that is not required much. So if you are interested, you can just check the proof. Right? So now I will do one example how to find the inverse modulo n using this method. Right? Using this method. What to do? Find an inverse of 5 modulo 7. Now, how do you ensure that inverse exists? Because GCD of 5 and 7 is 1. So, inverse modulo 5 exists. And inverse of 5 modulo 7 exists. Right? So, we know that GCD of 5, 7 is 1. We have GCD of 5, 7 is equal to 1. Now, what is your next job? We have to do that GCD can be expressed as a linear combinations of that. So that method will do. So 7 is equal to what we'll do? 5 times 1 plus 2. We'll do one more time. So 5 is equal to 2 times 2 plus 1. We need to have, because still we did not get 0. So 2 is equal to, we have 1 into 2 plus 0. So I got a remainder 0. Now using this Euclidean algorithm, we can have that this 1 is the GCD. So 1 is equal to, I can have 5 minus 2 into 2. Then as a linear combination of 5 and 7 I need. So this 2 I have to replace by taking the help of this 2. So 5 minus 2, the value of 2 I'll write first, which is 7 minus 5. 5 into 1, so I'm writing 5 into outside there is a 2. Now this I will get it as 5 times this 2 plus, okay, that I will write that into 5 times 2 minus 7 into 2. So I will have 5 into 3 plus 7 into minus 2. So we have written GCD as a linear combination, right? So what does it mean? Therefore, I have, from this I will get that 5 into 3 plus 7 into minus 2 is congruent to 1 modulo 7. This I can have. Now, as you discussed, that this value minus 1 is divisible by 7. But here 7 is a factor, right? This 7 can be omitted. So therefore, I can always say that 5 into 3 is congruent to 1 mod 7. Why? Because 7 is already there in this case. So this part can be, whole part can be omitted. So we'll say that 5 into 3 is congruent to 1 modulo 7. Done. Now this is what? This is the definition of inverse of 5 modulo 3. So what is the inverse? So 3 is the inverse of 5 modulo 7. So therefore, the final answer is equal to 3. So 3 is an inverse of 5 modulo 7. I hope you understand. Clear? So only thing is that you have to check how do you ensure that inverse exists. Whenever you have the GCD between the numbers, GCD of any two number a and n, if it is 1, always inverse of a modulo n exists. I hope you understand that. So you practice similar kind of problem, several problem if you practice, then it will be very clear to you. Up to that, I thought to discuss. So all the content I have taken from this book. I hope these videos are helpful. We'll come up with a new video in the next lecture. Thank you very much. Bye-bye.